Hey fellow nerds, today we are going to discuss some wave shaping circuits. We will start with the transient response of an RC circuit and then move on to first order RC high pass filter, first order RC low pass filter, RC differentiator and RC integrator. To learn the transient response, let us start by taking an RC circuit. I have a resistor of resistance R, I have a capacitor of capacitance C. They are connected in series and I have applied a potential V across them. When we say transient response, it means the behavior of the circuit right after the switch is on. Let us consider that the capacitor is initially uncharged. Now, when the switch is closed, the applied voltage V will appear across the resistance and the capacitor. So we can write V is equal to VR plus VC. If we take I to be the current passing in the circuit, the potential drop across the resistor will become I multiplied by R. Plus, we need the potential drop across the capacitor. Let's find it this way. We know current through a capacitor is given by C dV by dt. From here we can write dV is equal to I divided by C dt. Let's integrate on both sides. Integral of dV is V. This is equal to 1 by C is a constant. It doesn't depend on time. So let us keep it outside. Integral I dt. So potential across the capacitor is 1 by C integral of I dt. Let's write that here. So we get V is equal to IR plus 1 by C integral I dt. Let us differentiate both sides of this equation. On the left hand side we have V. V is the applied voltage, it is a constant. So if you differentiate it, you get 0. This is equal to, on the right hand side there is IR. R is a constant, so if you differentiate it, you will get R di by dt plus 1 by C. Derivative of integral of I dt is simply I. Let's divide the entire equation by R. So we get 0 is equal to di by dt plus 1 by RC I. Or we can write di by dt plus 1 by RC I is equal to 0. This is a first order differential equation. So the circuit we have over here is a first order circuit. The solution for such a differential equation is of the form I is equal to C e raised to minus t by RC. C here is a constant, not the capacitance, which we have to find out. For that, let us find the model of this circuit when t is equal to 0, which means when the switch has just closed, what does the circuit look like? We know initially the capacitor is uncharged. So when we just switch it on, the current through the capacitor will be really high. We have learned it in the previous video. This is how current through the capacitor changes. It is really high at first and then it exponentially decreases. So at t equal to 0, when the switch is just on, current through the capacitor is really high. So we can assume the impedance offered by the capacitance is really small, which means we can model the capacitor to be a closed circuit. Then the circuit will look like this. I have taken the current flowing through the circuit at t equal to 0, I naught. From this circuit, we can easily write the expression for I naught. I naught is V divided by R. So we get at t equal to 0, current is I naught and it is equal to V by R. But we have an expression for current. It is C e raised to minus t by RC. Again, I have to say this C over here is a constant and this is our capacitance. To eliminate the confusion, let me call the constant K. We have I is equal to K e raised to minus t by RC. When t equal to 0, current is V by R. So V by R is equal to K e raised to t is 0, so e raised to 0. Or V by R is our constant K. This means The current in the circuit can be written as V by R e to the power minus t by RC. All I have done is I took the expression for I and replaced K with V by R. Now let us write an expression for the potential drop across the resistor, that is VR. VR is I multiplied by R according to Ohm's law. So here we can write VR is equal to I is V by R multiplied by e raised to minus t by RC. We have to multiply this by R. R and R gets cancelled. So VR is V e raised to minus t by RC. Let us also find an expression for VC, the potential across the capacitor. We know applied potential is the sum of potential across the resistor and that across the capacitor. So potential across the capacitor will be V minus VR. Or we can write V minus V e raised to minus t by RC. Let us take V in common. So we get Vc is equal to V multiplied by 1 minus e raised to minus t by RC. We got three equations. I is V by R e raised to minus t by RC. VR is V e raised to minus t by RC. Vc is V multiplied by 1 minus e raised to minus t by RC. I can see one thing in common in all of these equations. It is RC. RC is called the time constant. It is denoted by tau. So tau is equal to RC. Wait, RC is the product of the resistance and the capacitance. How did we directly associate it with time? If you look at these equations, T by RC is the exponent of E. In mathematical expressions, exponents should always be dimensionless, which means T by RC should be dimensionless. If T by RC is dimensionless, then dimensions of T should be equal to dimensions of RC. Dimensions of T is T because T is time. So dimensions of RC should also be T. So it's only fair that we associate RC with time. Well, you could also think like this. Dimensions of resistance are M, L to the power 2, T to the power minus 3, I to the power minus 2. Also, dimensions of C are M to the power minus 1, L to the power minus 2, T to the power 4, I to the power 2. You can clearly see if you take the product of these two, M and M inverse will get cancelled, L square and L raised to minus 2 will get cancelled, T raised to minus 3 and T raised to 4 will give you T, I raised to minus 2 and I square will also be cancelled. So the dimensions of the product of R and C is T. That justifies why we are connecting the product of resistance and capacitance to time. Now, what is the significance of time constant? Time constant characterizes the rate at which the capacitor charges or discharges. For example, let us see what happens when one time constant has passed. That means T is equal to tau. We know I is given by V by R e raised to minus t by RC, but let's write RC as tau now. At this moment, t is tau, so this will become e raised to minus tau by tau, which is e raised to minus 1. If we calculate e raised to minus 1, we get this is equal to 0.368 V by R. Or we could say I becomes approximately equal to 37% of V by R. But what is V by R? V by R is I naught or our initial current, which is really high. So we could say when one time constant has passed, the current will become 37% of its maximum value, which is I naught. Let's see what happens to the potential across the capacitor. Vc is given by V multiplied by 1 minus e raised to minus t by tau. Here t is equal to tau, so this becomes e raised to minus 1. If we calculate e raised to minus 1 and take 1 minus e raised to minus 1, this will become 0.632 times V. Now, what is V? V is the applied potential. That is the maximum possible value of potential. When one time constant has passed across the capacitor, we will have approximately 63% of the maximum value of potential V. Now, let's see what happens when 5 time constant has passed. That is at t is equal to 5 tau. Here, I will be equal to V by R e raised to minus t by tau. But t is 5 tau. So here we get e raised to minus 5. If we calculate e raised to minus 5, this becomes 0.0067 times V by R, which is really small. So we could say this is approximately equal to 0. The current in the circuit is approximately equal to 0. What happens to the potential across the capacitor? Vc is V multiplied by 1 minus e raised to minus t by tau. Here t is 5 tau, so we get e raised to minus 5. If we calculate this, Vc will be 0.993 times V. Or we could say 99.3% of the maximum value. Let us take it to be approximately equal to V. We can conclude that after about 5 time constants is passed, almost all of the applied voltages dropped across the capacitor. So the capacitor now is acting as an open circuit and the current in the circuit has now become 0. We call this the steady state condition. Let us now plot how current in the circuit varies with time constant. Initially, when the switch has just been closed, current is really high, but after about 5 time constants, the current has become almost equal to 0. Let us also plot the potential across the resistor and the potential across the capacitor against the time constant. Initially, when the switch is just closed, across the capacitor we have 0 potential. We have seen the behavior of a capacitor in the previous video. As time passes, the potential across the capacitor increases. After about 5 time constants, it is completely charged. All of the applied potential is now seen across the capacitor. The exact opposite happens to the resistor. Initially, when the switch is just closed, capacitor is acting as a closed circuit, so all of the applied voltage is on the resistor. But then, as the capacitor gets charged, potential across the resistor decreases exponentially, and after about 5 time constants, it is almost equal to 0. Now that the concept is clear, let us go to our first wave shaping circuit, the first order RC high pass filter. It is first order because the differential equation that defines this circuit is of first order. It is a simple RC circuit. There is a resistance of resistance R. There is a capacitor of capacitance C. Input is applied over here. Output is taken across the resistor. Current flowing through the circuit is taken to be I. Now, the capacitive reactance XC is given by 1 by omega C. Capacitive reactance is the property of the capacitor that is analogous to the resistance of a resistor. Capacitance is not analogous to resistance. Capacitive reactance is analogous to resistance. It is 1 by omega C, so we can say it is inversely proportional to omega. Omega is the frequency of our input waveform. Since it is inversely proportional to omega, if omega is really high, then xc will be really small. If omega is really small, xc will be really high. When the reactance is too low, we can model the capacitor to be a closed circuit. When the reactance is really high, we can model it to be an open circuit. So we can say a capacitor offers high reactance to low frequencies and blocks them. Because high reactance means the capacitor is almost an open circuit. Also, it offers little reactance to high frequencies and passes them. Passes because at high frequencies, capacitor is almost just a closed circuit. Let us draw the circuit model for low frequency input signal. Since capacitive reactance is inversely proportional to the frequency, when frequency is really less, capacitive reactance will be really high. So we can model the capacitor to be an open circuit. The circuit model will look like this. Since it is open here, no current will pass through the circuit. That means the potential drop across the resistance R will be 0. V output is taken across the resistance R. So here we can write V output is equal to 0. Now let us draw the circuit model for high frequency input signals. When frequency is really high, capacitive reactance will be really low. So we can model the capacitor as a closed circuit. The circuit model will look like this. Here the V input is directly applied across the resistor and the output is also taken across the resistor. So we can write V output is equal to V input. When the input is a low frequency signal, output is 0, which means the low frequency signal did not pass through the circuit. When the input is a high frequency signal, V output is equal to V input, which means the high frequency signal was allowed to pass through it. Now, this is the idea of a high pass filter. It passes high frequency signal and blocks the low frequency ones. For example, let me take this periodic signal x of t. We know all periodic signals are basically sum of sinusoids. This particular periodic signal is actually the sum of a low frequency sinusoid and a high frequency sinusoid. Now, let's take a high pass filter. I am going to give x of t as an input. X of t is the sum of a low frequency signal and a high frequency signal. The low frequency component will experience high reactance from the capacitor and the high frequency component will experience less reactance. So in the output, we will only get the high frequency component. Let me repeat. This is the idea of a high pass filter, but it is too optimistic, don't you think? High frequencies will pass through, low frequencies will not pass through. The first question that comes to my mind is, how do we decide which frequencies are high and which frequencies are low? You could say that we could consider a particular value of frequency to be the cutoff frequency. If the frequency is greater than that, we'll consider it high. If the frequency is less than that, we'll consider it low. Agreed. For example, let us take 50 kilohertz to be our cutoff frequency. Consider 50.001 kilohertz and 49.999 kilohertz. This is higher than the cutoff frequency. This is lower than the cutoff frequency. Will this one get zero reactance and this one get infinite reactance? Practically, these two frequencies are very close to each other. So ideally, they should be experiencing the same reactance. If this can pass through, this will also pass through. If this cannot pass through, this also cannot pass through. So how does this work? That is why I said whatever we learned about high pass filter till now is the idea of it. Let us see how effectively we can implement this idea in reality. I'll take a high pass filter, which is just an RC circuit, and I'll give a sinusoidal input to it. First, I want to find the impedance of this circuit. It will be R plus the impedance of the capacitor is 1 by j omega c. We saw that in the last video. We have already called 1 by omega c xc, so let us replace it by that. Should we really keep 1 by j here? 1 by j is minus j, so we can write minus j xc. So total impedance of the circuit is R minus jXc. R is the resistance, Xc is the capacitive reactance. And minus J shows the phase difference between R and Xc. Now, using this, I want to write the current flowing through the circuit. Here we can use Ohm's law. Usually when we use Ohm's law, we write V is equal to IR. But this is only when we are exclusively considering the resistor. Here our circuit has a resistor and a capacitor. So we cannot write V equals IR, we'll have to write V equals IZ, Z being the impedance of the circuit. So here the current in the circuit will be input voltage divided by Z. V input divided by R minus JXC. Output is taken across the resistor. So I can write V output is actually the potential across the resistor. That is I multiplied by R according to Ohm's law. But we already found an expression for I. So I can write this is equal to V in divided by R minus JXC multiplied by R. I want to put R over here and take V in out. Now let us define something called voltage gain. Voltage gain is the output voltage divided by the input voltage. We already found output voltage is input voltage multiplied by R minus JXC. So V out by V in will be R divided by R minus JXC. Let us divide the numerator and the denominator by R. So we get this is equal to 1 by 1 minus j xc divided by r. This is our gain. Gain is denoted by the letter A. So we can write A is equal to 1 by 1 minus j xc divided by r. But xc is 1 by omega c. So instead of this, I want to write 1 by 1 minus j divided by omega c r. Again, omega is 2 pi times the frequency. So I want to write j divided by 2 pi FCR. Now, V out divided by V in is A. So I can write V out is A multiplied by V in. Now, A is complex. It has a J term in it, which means it has a magnitude and a phase. So when we multiply the input voltage with A, its amplitude will change as well as its phase. But the shape of the wave is going to be the same. If you started with a sine wave, it will still be a sine wave with a new amplitude and a new phase. Now, how much does the amplitude and phase change? Well, that depends on A, right? And what does A depend on? A depends on F, C, and R. But R and C are fixed. They are the capacitance and resistance in the circuit. F is the frequency of the input signal. So we can say gain depends on the frequency of the input signal. So how much does the amplitude and phase change? That depends on the frequency of the input itself. Let us write it down this way. Output will have the same wave shape, but it will differ in amplitude and phase angle depending on the frequency of the input signal. Depending on their frequencies, different input signals will experience different gains. So we got the expression for gain of the high pass filter. It is 1 divided by 1 minus j by 2 pi FRC. Gain depends on the frequency of the input signal. Let me give you a silly example. It is not even remotely related to a high pass filter, but it will give you an idea. Assume that for a signal x of t, due to whatever frequency it has, gain is equal to 0.001. For another signal y of t, for whatever frequency it has, gain is equal to 2. Now, in the output, x of t will come as 0.001 times x of t. Y of t will come as 2y of t. Obviously, you will not be able to find x of t there because 0.001 is almost equal to 0. This is how it works. For low frequency signals, gain will be really less. For high frequency signals, gain will be really high. So the low frequency ones will get erased in the output and the high frequency ones will be retained. Now we consider the input signal to pass through the high pass filter if its output power is at least 50% of the input power. That means the gain for this particular signal has not decreased its power less than 50%. Here the output is taken across a resistor And we know power dissipated across a resistor is proportional to the square of the voltage across it. Now, since output is taken across the resistor, whatever is the voltage across the resistor is our output voltage. So we can write VR squared is actually equal to V out squared. So the output power is proportional to square of the output voltage. According to the condition, output power should be at least equal to half of the input power. That means output voltage should be at least equal to 1 by root 2 times the input. V output should at least be 1 by root 2 times V input. The gain should not decrease the input voltage by anything less than 1 by root 2. In that case, we consider it not passed through the high pass filter. Otherwise, we can consider it as passed through the high pass filter. Now, this gives us a criteria to decide which frequency is high and which frequency is low. Now, the minimum frequency that will pass through the filter is called the cutoff frequency. We said the output voltage should at least be 1 by root 2 V input. So the cutoff frequency is that frequency where the output voltage is the critical value, that is 1 by root 2 times the V input. So we can write at cutoff frequency V output has the minimum required value, that is V input divided by root 2. Or we can write V output divided by V input will be 1 by root 2. 1 by root 2 is 0.707. Let us again take the expression for the gain. A is 1 divided by 1 minus j divided by 2 pi FRC. We have the frequency here. It is the frequency of the input signal. Now, at very high frequencies, 1 by 2 pi FRC will become approximately equal to 0 because f is really high and it is in the denominator. So, in the equation of gain, we can ignore this term. Then, gain becomes equal to 1. But gain is V out divided by V in. So we can write output voltage is equal to input voltage. This makes sense because we are dealing with a high pass filter and it is known to let high frequency signals pass through it without any problem. As the frequency gets lower, the gain will also get lower. The maximum value gain can get is 1 and the maximum value V output can get is V input. If we plot the output voltage against the frequency of the input voltage, we'll get a graph that looks like this. We call this the frequency response. At very high frequencies, it reaches the maximum value, and we know the maximum value for output voltage is input voltage. Let us mark it on the graph. Now, I want to mark the point where the output voltage becomes 0.707 times of input voltage. We learned that the frequency at which this happens is the cutoff frequency. So let us mark the cutoff frequency as well on the graph. I am calling it F0. The high pass filter will stop every signal that has a frequency which is less than F0 and it will pass every signal that has a frequency greater than F0. So we call the band of frequencies between 0 and F0 the stop band and the band of frequencies greater than F0 is called pass band. Let us now define cutoff frequency in a different unit. The decibel denoted by dB is a logarithmic unit and it is used to express ratios. If we talk in terms of power, decibel is denoted as 10 log to the base 10 P output divided by P input. But we have considered that at cutoff frequency, output power should be half of the input power. If we substitute that, we get the decibel value to be 10 log to the base 10 of P out by P in is 1 by 2 or 0.5. If we calculate this, we get minus 3.01. We could say this is approximately equal to minus 3 decibels. So at the minus 3 dB point, the output power is 3 decibels lower than the input power or 50% of the input power. Because of this reason, cutoff frequency is also known as 3 dB frequency. Let us mark that on the graph. In the expression for gain, here we have 1 by 2 pi FRC. I am going to take 1 by 2 pi RC out from it. I'll give it a name. I'll call it F1. 1 by 2 pi RC. R is the resistance, C is the capacitance. Why did I associate this with frequency? We already saw RC has the dimensions of time. So 1 by RC will have the dimensions of frequency, and 2 pi is just a constant. So justifiably, I can associate this with a frequency. I will call it F1. Then A becomes 1 divided by 1 minus J F1 by F. I can write the magnitude of A. It will be 1 divided by magnitude of the denominator will be root of 1 plus F1 by F squared. Why? Because the denominator is of the form A plus JB. Its magnitude is root of A square plus B square. That's exactly what I did here. I also want the phase of the gain. Since 1 minus j f1 by f is in the denominator, I'll have a negative tan inverse of imaginary part divided by real part, that is minus f1 by f divided by real part is just 1. Now the minus here and minus here can get cancelled. So phase angle is tan inverse of f1 by f. Let's try something. What happens as f tends to be infinite? If f becomes infinite, that is the input signal has a frequency that is very high, f1 divided by f will become 0. So this term will become 0 and we get magnitude of A is equal to 1. We have already seen this. Now what happens as input frequency becomes f1? In that case, magnitude of A will become 1 divided by root of 1 plus f1 is equal to f. So f1 by f will become 1. It's just 1. This is equal to 1 by root 2. Output voltage will become 1 by root 2 times input voltage. When does that happen? When the input frequency is cutoff frequency. Here the input frequency is f1. So f1 has to be our cutoff frequency. But f1 is 1 by 2 pi RC. So I can write the cutoff frequency f0 is nothing but 1 by 2 pi RC. Again, at cutoff frequency, the frequency of the input signal f is equal to f0. Or we can write f is equal to 1 by 2 pi RC. Take R to the left hand side and F to the right hand side. Then we get R is equal to 1 by 2 pi Fc. 2 pi F is omega. Let us replace it by that. Now 1 by omega C is Xc, the reactance of our capacitor. So we can say at cutoff frequency, capacitive reactance is equal to the resistance. Let's go to the next circuit. The first order RC low pass filter. It is first order because the differential equation that defines this circuit is of first order. This is also a simple RC circuit. It has a resistor of resistance R, capacitor of capacitance C. Input is given over here. The only difference it has from the high pass filter is that the output is taken across the capacitor instead of the resistor. Let us revisit the behavior of a capacitor. Capacitive reactance Xc is 1 by omega C. It is inversely proportional to the frequency. Because of that, a capacitor offers high reactance to low frequencies and blocks them. It offers little reactance to high frequencies and passes them. Let us draw the circuit model for low frequency signals. When the frequency is low, capacitive reactance will be high. That means the capacitor can be modeled as an open circuit. The circuit model will look like this. Since the circuit is open, no current will flow through it. That means the potential drop across the resistor is 0. Whatever is given at the input will be seen at the output. So we can write V output is equal to V input. Now let us draw the circuit model for high frequency input signal. When the frequency is really high, capacitive reactance will be really low. That means we can model the capacitor to be a closed circuit. The circuit model will look like this. Output is taken like this. So we can write V out is equal to 0. Let us see. When the input signal has low frequency, input is coming at the output. When it has high frequency, the output is 0. So low pass filter blocks high frequency signals and it lets the low frequency ones pass through it. Let us take the periodic signal x of t again. It is the sum of a low frequency sinusoid and a high frequency sinusoid. If we take a low pass filter and give x of t as an input, the output will have the low frequency component. The high frequency component will be stopped by the low pass filter. Again, this is the idea of a low pass filter. It is too good to be true, right? So we have to learn how this idea can be implemented practically. I will take a low pass filter and give a sinusoidal input to it. Again, let us start with the impedance of the circuit. Here also we have a resistor and a capacitor in series. So we can write impedance Z is R minus JXC. So using Ohm's law, I can write the current in the circuit is V by Z, that is V input divided by R minus JXC. Now I need the output voltage. Here the output is taken across the capacitor, so output voltage will be the voltage across the capacitor. According to Ohm's law, it is I multiplied by the impedance of the capacitor, that is minus JXC. We already have I over here. Using that, V output becomes V input divided by R minus JXC multiplied by minus JXC. Let us take V input out and minus JXC can go here. Again, let us define the voltage gain A to be V output divided by V input. Here we got V output is minus JXC divided by R minus JXC multiplied by V input. So V output divided by V input will be minus JXC divided by R minus JXC. Let's divide the numerator and the denominator by minus JXC. Then this becomes 1 divided by minus R divided by JXC plus 1. In the denominator, we have minus R by JXC plus 1. We can write it like this, 1 minus R by JXC. So we get gain A is equal to 1 by 1 minus R divided by JXC. We know XC is 1 by omega C. In the denominator, we will get 1 minus omega C R divided by J. Do we have to keep J in the denominator? 1 by J is minus J, but then we already have a negative over here. So if we bring J to the numerator, it will become 1 plus J omega C R. Again, omega is 2 pi times the frequency. Let us replace it by that. So we get the expression for gain 1 by 1 plus J 2 pi FCR. Let's put it in a box. Again, we can write A is V output divided by V input. So V output is actually A multiplied by V input. And A is complex. It has a J term. That means when we multiply the input signal with A, its amplitude will change, its phase will also change. And what does the change depend on? It depends on the gain A. And what does the gain depend on? It depends on the frequency of the input signal. Let's write it down. Output will have the same wave shape, but it will differ in the amplitude and the phase angle. The difference will depend on the frequency of the input signal itself. So depending on their frequency, different signals will experience different gains for the same circuit. We consider a signal to pass through the low pass filter if its output power is at least 50% of the input power. But power associated with the capacitor is proportional to square of the voltage across it. I am taking the voltage across the capacitor because here our output is taken across the capacitor. So VC square is equal to V out square. That means power is proportional to square of the output voltage. According to the condition, P output should be greater than or equal to half of P input. Since power is proportional to the square of V output, we could say V output is proportional to the root of the power. So we can write V output should be greater than or equal to V input divided by root 2. That is, the output voltage should at least be 1 by root 2 times the input voltage. Or by taking V input to the other side of this inequality, we can write V output by V input should be greater than or equal to 1 by root 2. But the ratio of output voltage to the input voltage is our gain. That means the gain should be greater than or equal to 1 by root 2. Let's take a look at the expression for gain. We have we have the frequency over here. If frequency becomes really high, let's say f tends to infinity, since f is in the denominator, a will become 0. So for high frequencies, gain is 0. As you lower the frequency, gain will increase. At a certain low frequency, you will get the gain to be equal to 1 by root 2, which is the minimum required value of A. If you keep decreasing the frequency, gain will increase and we are good. But if you take any frequency that is greater than this particular frequency, gain will be less than 1 by root 2. So there is a maximum value of frequency that you can take. We call it the cutoff frequency of the low pass filter. Cutoff frequency is the maximum frequency to pass through the filter. At the cutoff frequency, gain will be equal to 1 by root 2 or 0.707. That means V output divided by V input will be equal to 0.707. Or we can write V output should be 0.707 times V input. Let us again take the expression for the gain. It is 1 by 1 plus j 2 pi FCR. Here we have 2 pi FCR. At very low frequencies, we can consider 2 pi FCR to be approximately equal to 0 because f has a really small value. In that case, gain will become 1 divided by 1 plus 0 or gain is equal to 1. But gain is V output divided by V input. So we can say V output is equal to V input. That is, at very low frequencies, gain takes the maximum value, which is 1, and output will be exactly equal to input. If you keep increasing the frequency, the denominator in this expression will increase and gain will decrease. If we plot the output voltage against the frequency of the input voltage, this is how it will look like. At very low frequencies, the output is equal to the input. Let us also mark the point where the output becomes 0.707 times V input. Now the frequency corresponding to this will be our cutoff frequency. Let us mark it on the graph. I am calling it F0. We can see that whenever the frequency of the input is less than F0, the signal will pass through the filter. So the band of frequencies from 0 to F0 will be the pass band. If the frequency of the input signal is greater than F0, it will not pass through the filter. So the band of frequencies where the frequencies are greater than F0 is called the stop band. When we discussed high pass filter, we saw that the decibel value corresponding to output power being half of the input power is -3. The same math is applicable here also. We can call the cutoff frequency 3 dB frequency. Let me mark it on the graph. In the expression for the gain, over here we have 2 pi FCR. I am going to take 2 pi CR out of it and take its reciprocal. I have 1 by 2 pi RC. I am going to call it F2. We already saw why I am associating this with a frequency because 1 by 2 pi RC has the dimensions of frequency. Now, A over here can be written like this 1 divided by 1 plus J 2 pi FCR. I will write it like this F divided by 1 by 2 pi CR. 1 by 2 pi CR or 1 by 2 pi RC, we are calling it F2. Then A can be written like this 1 by 1 plus J F divided by F2. I want the magnitude of A. Numerator is just 1 divided by denominator is of the form A plus JB whose magnitude is root of A square plus B square. So here I can write root of 1 plus F by F2 whole square. I also need the phase angle. We know phase of A plus JB is tan inverse of B by A. Now, what we have over here is of the form 1 by A plus JB. Its phase is minus tan inverse of B by A. So here we get minus tan inverse of F by F2 divided by 1. Let us see what happens to the magnitude of the gain as the frequency of the input tends to be 0. If f becomes 0, f by f2 is 0. So magnitude of A becomes 1. That means at the lowest frequencies, gain takes its maximum value. Now let us see what happens to the magnitude of the gain as f becomes f2. If f becomes equal to f2, f by f2 will become 1. Then magnitude of gain will become 1 divided by root of 1 plus 1, which is 1 by root 2. But we already said when the gain becomes 1 by root 2, the frequency is called cutoff frequency. That means f2 has to be our cutoff frequency. But we took f2 to be 1 by 2 pi RC. So the cutoff frequency f0 is given by the expression 1 by 2 pi RC. Let's put it in a box. Also, if we take f is equal to f0, we can write f is equal to 1 by 2 pi RC. Let us take f to the other side of the equation and r to this side of the equation. 2 pi f is omega. Let us replace it by that. Now, on the right hand side, we have 1 by omega c. It is the capacitive reactance. Let's replace it by xc. So we get at cutoff frequency, capacitive reactance is equal to the resistance of the circuit. Let us take the next circuit. It is the RC differentiator. This is again a simple RC circuit. We have a capacitor of capacitance C. We have a resistor of resistance R. Input is given over here. Output is taken across the resistor. Isn't this the exact circuit for a high-pass filter? Yes, it is. We are going to learn how we can use a high-pass filter as a RC differentiator. First, let's write down the conditions a high-pass filter has to satisfy so that it can work as an RC differentiator. The first condition is that the time constant RC of the circuit should be smaller as compared to the time period of the input signal. RC should be very much less than T, which is the time period of the input signal. We have seen previously that a capacitor requires at least 5 time constants to completely charge and discharge. So if the time constant is smaller, the capacitor will charge and discharge faster, which means the circuit will respond to the input faster. The fast response makes sure that the output closely follow the rate of change of the input. The second condition is that value of capacitive reactance should not be smaller than 10 times the R. That is, Xc should be greater than or equal to 10 R. Or we can write 1 by 2 pi fc is greater than or equal to 10R. 1 by 2 pi fc is just another expression for xc. Why are we doing this? See, in the circuit we have two elements. One is a resistor, one is a capacitor. If the reactance of the capacitor is really higher than the resistance of the resistor, most of the input voltage will drop on the capacitor. It is like having a very large resistance and a very small resistance in series. Let us say 99 ohm and 1 ohm. If you apply a potential of 100 volt across them, this one will get 99 volt and this one will get 1 volt. Here we want most of the voltage to drop across the capacitor, so we make sure its reactance is very much greater than the resistance. But we are taking the output across the resistor. Then why do we want most of the input voltage to drop on the capacitor? Let me show you the reason mathematically. Using KVL, we can write applied input voltage will be potential drop across the capacitor plus potential drop across the resistor. But if Xc is very much greater than 10 times R, potential across the capacitor will be very much larger than potential across the resistor. So we can say this is approximately equal to just Vc. Now let us try to find an expression for the current in the circuit. Current in the circuit is I. This is the same current that is passing through the capacitor. For a capacitance with a potential difference Vc across it, current is given by C dVc by dt. But we just found Vc is approximately equal to V in. So we can write I is C dV in divided by dt. Now let us find the output. V output is taken across the resistance R. So according to Ohm's law, it will be I multiplied by R. But I is C dV in divided by dt. This multiplied by R. So we get V output is RC multiplied by dV in by dt. Which means the output voltage is proportional to derivative of the input voltage. This is why we call this circuit our RC differentiator. We got this expression as the output only because we took Vc is approximately equal to V in. We got Vc is approximately equal to V in only because we took Xc is very much greater than 10 times R. So that is the justification for the second condition. Now let us take a sinusoidal input and see. As an example, I will take the input to be V0 sine omega t. Now, an RC differentiator is just a high pass filter. I know the expression for its gain. A is 1 by 1 minus j f0 by f. But f0 is 1 by 2 pi RC. So we can write 1 by 1 minus j 1 by 2 pi RC f. 2 pi f is omega. Let us replace it by that. Then we get gain is 1 by 1 minus j 1 by omega RC. Magnitude of the gain is going to be 1 by root of 1 plus 1 by omega RC squared. Phase is going to be tan inverse of 1 by omega RC. We saw all of these in the high pass filter section. Let's call the phase theta. Now the output of the circuit is going to be input multiplied by the gain. Multiplying the input by the gain will change its amplitude by this much and phase by this much. So we can write V output is equal to 1 by root of 1 plus 1 by omega RC squared multiplied by V0. This will be the new amplitude. Sine of omega t plus theta. Theta is the phase that is added by the gain. We want our circuit to be a differentiator. And we just learned for a differentiator, the output is equal to RC multiplied by derivative of the input. Here we have taken V naught sine omega t as the input. So the output should be RC multiplied by derivative of the input, that is V naught omega cos omega t. We got the general expression for the output. It is this. Over here we have sine omega t plus theta. If our circuit is a proper differentiator, this should become cos of omega t. That is possible if theta is 90 degree. So we can write for proper differentiation, theta should be 90 degree. Let us take theta to be equal to 90 degree. Then tan of theta will become infinite. We already have the expression for theta. It is tan inverse of 1 by omega RC. So tan theta will be 1 by omega RC. So here we get 1 by omega RC should be infinite. That means the denominator omega RC should be a really small value. So we can write omega RC is very much less than 1. Let us take omega C to the other side. Then we get the condition for proper differentiation is R is very much less than 1 by omega C. That is, the resistance in the circuit should be very much lesser than the capacitive reactance. Let us see what happens to the magnitude of the gain if R is very much less than 1 by omega C. Magnitude is 1 by root of 1 plus square of 1 by omega RC. Let us multiply the numerator and the denominator by R. Then we get R divided by R root of 1 plus 1 by omega RC squared. In the denominator, let us take the R inside the root. Then it will become R square. The R square over here and the R square over here will get cancelled. Now the denominator is root of R square plus 1 by omega C whole square. But we have the condition R is very much less than 1 by omega C. So R square will be very much less than 1 by omega C whole square. So we can assume their sum is approximately equal to just 1 by omega C whole square. It is like writing 1 plus 10 raised to 6. We can write this is approximately equal to 10 raised to 6. So the magnitude becomes R divided by root of 1 by omega C square. But root of 1 by omega C squared is 1 by omega C. This is R by 1 by omega C. Let's bring omega C to the numerator. It becomes omega C R. So for the high pass filter to be a proper differentiator, phase of the gain should be 90 degree, magnitude of the gain should be omega CR. Let us substitute them in this equation. Then we get V output is equal to omega CR multiplied by V naught sine of omega t plus 90 degree. Sine of omega t plus 90 degree is cos of omega t. So we can write V output is RC V naught omega cos omega t. This is the output we were expecting. The next circuit is the RC integrator. Again, we have a resistor of resistance R and a capacitor of capacitance C. Input is given over here and output is taken across the capacitor. Yes, this is a low pass filter. Let us see the conditions a low pass filter has to satisfy so that it will become an RC integrator. The first condition is that the time constant RC of the circuit should be very large as compared to the time period of the input signal. RC should be very much greater than T. When RC is longer, the capacitor will take more time to charge and discharge. That is, the filter will react slowly to the changes in the input. The slow response will cause it to average, or we can say smooth out the input signal over time rather than following every small change that is happening in the input. Because of the smoothing effect, the output is going to be a value that is like the integrated result of the input. The second condition is that the value of R should not be smaller than 10 times the capacitive reactance. We take R to be greater than or equal to 10 times the capacitive reactance. Or we can write R is greater than or equal to 10 by 2 pi Fc. You can see that the first condition is actually just a consequence of the second one. Because if R is greater than or equal to 10 by 2 pi Fc, if I take C to the other side, I get RC is greater than or equal to 10 by 2 pi multiplied by 1 by F. 1 by F is the inverse of frequency of the input. That is the time period of the input. So we can write RC should be greater than or equal to 10 by 2 pi times time period, which means the time constant RC is very much greater than the time period of the input signal. Now, here we need the resistance to be very much higher than the capacitive reactance. So, most of the input voltage will drop across the resistor. Using KVL, we can write input voltage is equal to voltage drop across the resistor plus that across the capacitor. But here, most of the voltage drop is across the resistor, so this is approximately equal to VR itself. Now, I want the current through the circuit. Current through the circuit is I. This is the exact current that is passing through our resistance R. So using Ohm's law, I will be equal to VR divided by R. But we just took VR as approximately equal to V input. So I is approximately equal to V in divided by R. This is the current that is charging the capacitor. So the charge in the capacitor Q is going to be integral I dt. But I is V in by R, so we can write integral V in by R dt. 1 by R is a constant. Let's take it out of the integration. 1 by R integral V in dt. This is the charge in the capacitor at a time t. I want the output voltage. Output voltage is the voltage drop across the capacitor, Vc. But that will be charge divided by the capacitance. We already have an expression for Q over here. If you use that, V out comes out to be 1 by RC integral V in dt. That means V out is proportional to integral of the input. Let us give a sinusoidal input to our circuit. I'll take the input to be V0 sine omega t. Since the circuit is just a low-pass filter, I know the expression for its gain. A is equal to 1 by 1 plus j f by f0. f0 is 1 by 2 pi rc. If I substitute, this becomes 1 by 1 plus j 2 pi rc f. 2 pi f is omega. If I use that, this becomes 1 by 1 plus j omega rc. From this, I can write the magnitude of A. It will be 1 by root of 1 plus omega rc squared. I also want the phase. It will be negative of tan inverse omega rc. Let me call this theta. Now, output of the circuit will be input multiplied by the gain. Multiplying the input by the gain will alter its amplitude and phase. So, output of the low-pass filter is going to be 1 by root of 1 plus omega rc squared multiplied by V0. This will be the new amplitude, sine of omega t plus theta. Theta is the phase added from the gain. We want this low pass filter to act as an integrator. We know for an integrator, V output is 1 by RC multiplied by integral of the input. Here the input is V naught sine omega t. So the output should be 1 by RC multiplied by integral of V naught sine omega t. V naught divided by omega minus cos omega t. This can be written as minus 1 by omega RC V naught cos omega t. Here we need minus cos omega t. In the general equation that we found, we have sine of omega t plus theta. We want this to be minus cos of omega t. That will happen if theta is equal to minus 90 degree. That is, for proper integration, theta should be equal to minus 90 degree. Let us take theta to be minus 90 degree. That means tan theta will be minus infinity. We have the expression for theta here. It is minus tan inverse of omega RC. So tan theta will be minus omega RC. Here we get minus omega RC is equal to minus infinity, or omega RC should be infinite. That means omega RC is a number that is very much greater than 1. Let's take omega and c to the other side. We get R is very much greater than 1 by omega c. Resistance in the circuit is very much greater than the capacitive reactance. If this is the case, let us see what happens to the magnitude of the gain. Magnitude of the gain is 1 by root of 1 plus omega RC squared. Omega RC is a large number. So omega RC squared is an even larger number. We have 1 plus omega RC whole square. It is like adding 1 to a huge number like 10 raised to 6. This is approximately equal to 10 raised to 6 itself. So 1 plus omega RC squared can be written as omega RC squared. So the magnitude of the gain becomes 1 by root of omega RC squared. That is 1 by omega RC. So for proper integration, phase angle of the gain should be minus 90 degree and its magnitude should be 1 by omega RC. Let us substitute it in this equation and see what we get. V output becomes 1 by omega RC multiplied by V naught sine omega t plus theta is minus 90 degree, so minus 90 degree. Sine omega t minus 90 degree is minus cos omega t. So we get V out is 1 by omega RC multiplied by V naught multiplied by minus cos omega t. Let's take the minus from here and put it over there. Output is minus 1 by omega RC multiplied by V naught cos omega t. This is exactly the output we were expecting if the circuit is acting as an RC integrator. So that's all about it for today. See you in the next video. And don't forget to subscribe.